Welcome to aminacademy.com. In astronomy, let us discuss about motion of satellite and spacecraft. Now let us understand how an object such as satellite can be put into orbit around the Earth, and an object such as planetary probe can escape from orbit. How it's possible, we can discuss now. Newton's universal law of gravitation and Kepler's laws describe the motion of Earth satellites and interplanetary spacecraft as well as the planets. For example, Sputnik, the first artificial Earth satellite, was launched by what was then called the Soviet Union on October 4, 1957. Since that time, thousands of satellites have been placed into orbit around the Earth, and spacecraft have also orbited the moons, Venus, Mars, Jupiter, Saturn, and a number of asteroids and comets. Once an artificial satellite is in orbit, its behavior is no different from that of natural satellites, such as our moon. If the satellite is high enough to be free of atmospheric friction, it will remain in orbit forever. However, although there is no difficulty in maintaining a satellite once it is in orbit, a great deal of energy is required to lift the spacecraft off the Earth and accelerate into orbital speed. Now, further discussion. The motion of satellites around the Earth has the same characteristics as an object with circular motion. The velocity of the satellite directs along the tangent of the path. At the same time, the acceleration acts towards the center. What is a satellite? That means what are satellites? We will explain. Satellites are objects or bodies that revolve around a heavier body in space. There are two types of satellite. The first one, natural satellite. Satellites naturally present in space, such as comets and moon. Artificial satellite, a satellite made by humans for various purposes such as weather forecasting, communication, etc. Now you can find numerous natural satellites in space, and every planet has at least one of its natural satellites, where our Earth has only one, that is the moon. Other planets such as Jupiter are known to have 53 natural satellites, that is moons. Now, the motion of satellite around the Earth, how it's happened. A satellite orbiting the Earth has velocity and acceleration component similar to an object moving a circular path. While revolving around the Earth, satellites make a circular path. The tangent to this circular path gives the direction of the satellite's velocity, whereas acceleration is towards the center of the circle. Various forces act between the Earth and the satellite, making them orbit on a circular path. The net force that acts in the inward direction of the circle makes the satellite accelerate around the Earth. The gravitational force that acts between Earth and the satellite and centripetal force are two main forces causing the motion of satellite around the Earth. If there is no centripetal force, satellite will keep moving at the same speed and direction. In such case, the satellite will move on a straight path if there is no centripetal force, and there will be no circular motion. However, some satellites move along the elliptical orbit. In that case, unlike the circular motion, the central body is positioned at foci of the ellipse. As a result, the velocity component of the satellite acts along the tangent of the ellipse. At the same time, the acceleration acts towards the focus. As Newton's second law of motion, the direction of the net force will be towards the focus. Next, orbital velocity of a satellite. What is the velocity in orbital path? The velocity with which the satellite moves around the Earth is known as the orbital velocity of the satellite. Orbital velocity is also known as critical velocity. Finally, the minimum velocity is required to make a satellite move around the Earth with stability. What is escape velocity of the satellite? The escape velocity of a satellite is defined as the minimum velocity required by the satellite to escape the Earth's gravitational pull. Look at here. Suppose you are on the Earth surface. You are throwing a stone or object. Here it go, and after it comes towards the, because of the gravitational pull, it will fall some places here. If you throw still more velocity, it fall here. Like that, if you are throwing an object such a velocity that it won't pulled by the Earth gravitational, so it's form a straight path. After that, after gaining escape velocity, it's around the Earth with the particular angular velocity. That is called an escape velocity. Next one, interplanetary spacecraft. What is that? The exploration of the solar system has been carried out largely by robot spacecraft sent to the other planets. To escape Earth, these craft must achieve escape speed. That is, the speed needed to move away from the Earth forever, which is 11 km per second for the Earth, about 25,000 miles per hour. Such a big velocity we need to throw any body, and it won't come back to the Earth again. After escaping Earth, these craft coast to their targets, subject only to minor trajectory adjustment provided by small thruster rockets on board. In interplanetary flight, these spacecraft follows orbits around the Sun, and they are modified only when they pass near one of the planets. Now let us discuss about interaction of many bodies. That means we know that two bodies attract each other. We will discuss here more than two bodies, how it attract each other. As an example, suppose you have a cluster of thousands of stars all orbiting a common center. Such clusters are quite common, as we'll see in the star clusters. If you know the exact position of each star at any given instant, we can calculate the combined gravitational force of the entire group on any one members of a cluster. Knowing that force on the star in question, we can therefore find how it will accelerate. If we know how it was moving to begin with, we can then calculate how it will move in the next instant of time, thus tracking its movement. By using modern computing power, it's possible here to calculate the attraction forces between more than two or many bodies. These supercomputers at NASA's Ames Research Center are capable of tracking the motion of more than 1 million objects under their mutual gravitation. Discovery of Neptune. The discovery of the eighth planet, Neptune, was one of the high points in the development of gravitational theory. In 1781, William Herschel, a musician and amateur astronomer, accidentally discovered the seventh planet, Uranus. It happens that Uranus had been observed a century before, but in none of those earlier sightings was it recognized as a planet. Rather, it was simply recorded as a star. Herschel's discovery showed that there could be planets in the solar system too dim to be visible to the unaided eye, but ready to be discovered with a telescope if we just knew where to look. In 1790, an orbit had been calculated for Uranus using observation of its motion in the decade following its discovery. In 1843, John Couch Adams, a young Englishman who had just completed his studies at Cambridge, began a detailed mathematical analysis of the irregularities in the motion of Uranus to see whether they might be produced by the pull of an unknown planet that is called Neptune. So far we discussed about planetary motion and how the motion of satellites and spacecraft happening. We have done. Please subscribe our YouTube channel.